So we're still in Chapter 2, Trigonometric Functions, and this section we'll be talking about right triangle trigonometry. So make sure you're clear in your mind that this is all about right triangles. Then eventually we'll extend our study beyond right triangles. So the first objective is to find the values of trigonometric functions. So I'm going to write trig for short. Trigonometric functions of acute angles which are less than 90 degrees in size. The second objective is going to be to use the fundamental identities. So we'll learn about and then practice using the fundamental identities. The third objective is to find the values of the remaining trig functions given the value of one of them. So it's kind of like a puzzle. You're detectives. You get the value of one trig function and you can find the values of all the rest. And then the last objective is to use the complementary angle theorem. So we'll learn about it and then use it. So the first objective is to find the values of trigonometric functions of acute angles only to begin. So what is a right triangle? Recall that it's any triangle that has a right angle, a 90-degree angle, and we indicate that by putting a little square in the triangle. And it doesn't matter how the triangle is oriented. If one of the angles is a right angle, it's a right triangle. So recall from algebra that if you have a right triangle, and you know these side lengths, A, B, and C, that the Pythagorean theorem tells you that A squared plus B squared equals C squared. And there's hundreds of proofs of the Pythagorean theorem. If you Google that, you'll see. So let's define an acute angle technically. So we have this initial side, which as we said, we put on the positive x-axis. And then we have the side where the angle ends, that's called its terminal side. So the angle is this opening here. The angle is the part in between. And so if the angle is smaller than 90 degrees, so it's going to be sitting in quadrant 1, then it's an acute angle. So there's 6 ratios associated with a right triangle. So if you think about it, it's A to B, B to C, A to C, and then the reciprocals of all of those, B to A, C to B, and C to A. So these 6 ratios depend only on the size of the angles. Doesn't depend on the size of the triangle. They're a characteristic of the size of that angle. So let's look at 2 similar triangles. So recall that if you have one right triangle, so we know this is a right angle, and we draw another triangle, right triangle inside of it. Well, now we know that this angle is the same on both triangles, and these 2 angles are the same, so these 2 angles must be the same. So if the angles are all the same, they're called similar triangles. So there's 6 equations that come from comparing similar triangles. And recall that it's the ratio of corresponding sides that are equal. So what we know is that A to B must equal A prime to B prime. And A to C must equal A prime to C prime. And then B to C must equal B prime to C prime. So these are called proportions when you have 2 ratios that are equal. So then we also have the reciprocals, and these all have names. That we'll learn in a minute. So we have B prime to C prime, and then of course the reciprocals. So all of these ratios are equal. And hopefully you learned this in beginning algebra. That's where we teach it at Sierra College. So these ratios have names in the world of trigonometry. So the 6 ratios of a right triangle are called trigonometric functions. And here's how they're defined. So the sine of this angle theta is the ratio of the opposite side, B, to the length of the hypotenuse, C. So the sine is the opposite over the hypotenuse. So a lot of people use a little abbreviation to help them remember this. Then the cosine is defined as the length of the adjacent side over the length of the hypotenuse. So the cosine is the adjacent side over the hypotenuse. Then the tangent is the opposite over the adjacent. So a lot of people use this remembering device, SOHCAHTOA, to remember these ratios. If you make up your own remembering device, it will probably work even better. So then we have the cosecant, which is defined as C over B. So notice that's the reciprocal of sine. Who made this up? The cos don't go together here. And secant is the reciprocal of cosine. So that's how I remember these, of who's reciprocal of who. The cos don't go together. But then for tangent and cotangent, they do. So the cotangent is the reciprocal of tangent. So you have to memorize these. So I'd suggest flashcards or drilling each other. There's lots of ways to memorize. Use the way that works best for you. So here's a little table that you can see and work on memorizing these. So what do you observe about these functions? Which ones are reciprocals of each other? So sine and cosecant are reciprocals of each other. Cosine and secant are reciprocals of each other, and tangent and cotangent are reciprocals of each other. So since the a and the b and the c are all positive, each of the trigonometric functions of an acute angle has a positive value, but note that that won't always be the case. In trigonometry, we will be defining how can you have a negative number for your cosine, but we'll talk more about that. So we'll do these exercises together in class. So let me move on to use the fundamental identities. So we have some reciprocal identities, they're called, which we just talked about. Cosecant and sine are reciprocals of each other. Secant and cosine are reciprocals of each other, and cotangent and tangent are reciprocals of each other. So these are some of the fundamental identities that are called the reciprocal identities. Then we also have these quotient identities. So let's see, why is the tangent of theta equal to the sine of theta over cosine of theta? Well, let's see, sine of theta is opposite over hypotenuse, and cosine of theta is adjacent over hypotenuse. So if I do sine theta over cosine theta, it's opposite over hypotenuse over adjacent over hypotenuse. Divided by a fraction, we actually multiply by the reciprocal. So we see the h's cancel, and sure enough, we get opposite over adjacent, which is the tangent of theta. So in a similar way, the cotangent is the cosine over the sine. So you need to get very familiar with these identities. And then let's derive the Pythagorean identity. So we start with your old friend, the Pythagorean theorem, but then we're going to derive its counterpart in the trigonometry world. So we're going to divide both sides by c squared and see that you get a squared over c squared plus b squared over c squared equals 1. And then using properties of exponents, I can rewrite a squared over c squared as a over c quantity squared. And similarly with the b squared over c squared. So I get a over c squared plus b over c squared is 1. Well, look at this triangle and look at this theta. And a over c is the adjacent over the hypotenuse. So that's the cosine of theta. So I can rewrite it as cosine theta. And then the b over the c is sine theta. So the cosine of theta squared plus the sine of theta squared has to be 1 for any theta. We just derived that from the Pythagorean theorem, which we know is true. So this gives us one version of the Pythagorean identity, and it's more typically written as sine squared theta plus cosine squared theta equals 1. So this is a notation. When you have cosine of theta quantity squared, you can write it more conveniently as cosine squared of theta and read it how you just heard me say it. So this is the most important identity in trigonometry. We'll use it over and over and over and over. So let's figure out two other versions of it. If I have sine squared theta plus cosine squared theta equals 1, and I divide both sides by cosine squared theta, I'm going to get another familiar version of the Pythagorean identity. That's just a rearrangement. So sine squared over cosine squared is tangent squared plus 1 equals secant squared of theta. So here's another version. Tangent squared of theta plus 1 equals secant squared of theta. And notice that after every trigonometric function always comes an angle name. It must be there. So make sure you get in the habit of every time you write a trigonometric function that you write the name of an angle afterwards. So let's find the other variation of this by taking our Pythagorean identity and dividing both sides by sine squared theta. Then we're going to get 1 plus cosine squared over sine squared is 1 over sine theta quantity squared. So that gives us 1 plus cotangent squared of theta equals cosecant squared of theta. So make sure you're very familiar with these, and I don't memorize these two. I remember how to get them. So make sure you work on memorizing those. So we'll do these problems in class together, and let's move on to objective 3, which we'll also do in class together. And then objective 4 is to use the complementary angle theorem. And two acute angles are called complementary if their sum is 90 degrees. So it's just a word that's used to define two angles, which if you add their sizes together you get 90. They're called complementary. So since one of the angles in a right triangle is 90 degrees, the other two angles have to add to 90 degrees, since we proved to ourselves last class that all the angles in a triangle add up to 180 degrees. So if you're in a right triangle, the other two angles must be complementary. So let's look at a triangle and notice some relationships of if I have this angle beta and this angle alpha, which must be complementary to each other. The sine of beta is the opposite b over c. But if I look at it from alpha's point of view, that's adjacent over hypotenuse, which is the cosine of alpha. So look at all these relationships and notice that sine of beta is cosine of alpha. Cosine of beta is sine of alpha. So which functions do you think are co-functions? They're the ones whose names sound like co-functions of each other. So sine and cosine, secant and cosecant, and tangent and cotangent. So this is different than the reciprocal identities. These are called co-functions. So the complementary angle theorem tells us that co-functions of complementary angles are equal, which we just proved to ourselves. So this little table might come in handy, and it's much more useful in the future. It's not that useful in and of itself. The end of section 2.2.